Okay, so this is the second part of the kinetics relays notes, and just want to point some things out to you. Uh, we looked at one of the models where the slow step was actually the middle step, and I point out you're going to have to probably use substitution to actually get your rate law. So this is showing you how we would do that. So I have a fast step here, I have a slow step and a fast step. If I sit there and I think about this and I write out my rate law, here's my rate law for the first one. Here is my rate law for the second one. The problem with the slow step is this A2 right here. That A2 is a product in the first step, reactant in the second step, so it means the intermediate. So we need to do a substitution. So my rate of the forward reaction, which is the A2 raised to the first, is equal to the K rev, or the reverse reaction, of the 2A. Okay, so then what I'm going to do is I'm going to use my algebra. I want the A2 because that's what I need. Okay? Because I need to replace the A2. The A2 is the intermediate. So when I apply my algebra, I get A to the 2 equals to the K forward over K reverse of A2 raised to the first, or K A2 to the first. I'm simply going to sub this in for the A2, and when I do that, I get this expression for my rate law. And this is how we deal with intermediates, because we cannot write intermediates in the rate law. Okay, so then I wanted to bring this up as well, because sometimes they ask you about ozone layer. Ozone is a very special form of oxygen. It's O3. This is looking at the decomposition of ozone with and without the elemental chlorine form of chlorofluorocarbons. So here's my overall reaction. So not exactly the same. And I'm going to look here, and I just went through and I crossed off. I have oxygen on this side, oxygen on that side. Since it's a product here, reactant here, that's the intermediate. Okay, so my intermediate is 0. I don't have any that are product, or sorry, reactant, product. So I have no catalyst. When I look at this one over here, here I have ClO here, ClO4O here. Product, reactant, that's intermediate. Here I have Cl as a reactant. Here is a product. There's your catalyst. Okay. So then some of the things that get asked on this is, well, what's the proposed law if the first step is slow? So if I'm looking here, since I have a catalyst involved on this one, even though I haven't graphed or anything, the whole point of the catalyst is to make the reaction slower. I'm sorry, faster. So the most logical one that's going to have the first step as a slow step is probably this one. Because I have the catalyst. Okay? So when I write this rate law, I'm going to have K square bracket O3 raised to the first. Now it asks if the other one has a second step is slow, then how am I going to write that reaction, that rate law? So I put it over here in the margin. So my K forward is equal to O3 to the first. My K reverse is equal to the O plus O2. So when I divide that all out, I want to get the forward reverse, O3 to the first times O2 equals, O2 negative 1, and we're going to talk about what that means there, equals O to the first. O, when I manipulate it around, this is what O equals. Don't lose sight of that negative 1. The reason it's negative 1, because I brought it from here, I'm dividing it out, so I got to use my exponent rule. Okay, that's how it can become negative. So my rate for the slow step here is O3 and O. So I'm going to sub in for my O this expression. Don't forget you got negative 1 there. This becomes O3 squared, because I have 2 of them, times O2 negative 1. Now, it says based on experimental data, it's found that the rate law for the decomposition of ozone without chlorine is rate equals O3 squared O2 negative 1. Ozone is second order while oxygen inhibits the reaction. That's what that means. That means that's second order. Since this is a negative 1, that means that inhibits the reaction. Based on the experimental data, which step is the slow step? The second step. The second step is your slow step. And that has to do with that O2 having a negative 1. This is going to hinder it. That makes this your slow step. Okay? So based on your answer, we want to draw out what we have for our model. Since that O2 is going to hinder that second step, then this hump has to be larger than my first hump. Since this reaction, the first step was its fast step, then this is my taller hump, and the other one is below it. Now, I did keep the original graph behind it to show you the whole point of the callus. The callus is going to lower that activation energy. Makes it easier. Remember, the EA for these two humps equals the overall EA. A catalyst will lower those two humps slightly to make it easier for the reaction to progress. Without the will the reaction with Cl proceed faster or slower compared to the reaction without Cl? So if I don't have the catalyst, I want you to justify what's going to happen in reaction. So Cl is a catalyst which creates a reaction pathway with a lower activation energy, requiring less energy to successfully break bonds, resulting in more successful collisions. Then it asks you to write the proposed law if the first step is slow. And so if your first step is slow, so I'm going to have my Cl to the first, O3 to the first, because remember, it's the intermediates I can't write. And we've already sketched the graph. I've already talked about that. And hopefully, this has hopefully made a little more sense. The substitution part is usually where we get a little hung up on, but hopefully that clarified about what the 2 and the 1 and -1 and what that means and how that affects what we're graphing and how it affects the overall reaction.